Welcome to Statistical Computing using C and C++. Today, we are going to explore a fascinating and highly practical topic known as jumps in loops. When you write programs, you often use loops to repeat tasks. But what happens when you need to break the rules and stop early? That is exactly what we will learn today.
To begin, let us think about why this concept matters. Imagine you are reading a textbook chapter by chapter. Sometimes you find exactly the answer you need in chapter 2, so you stop reading the rest of the book entirely. Other times, you realize a specific section is boring, so you skip just that section and move on to the next one. In programming, loops are designed to repeat a block of code. However, real-world problems often require us to break these rules based on new information. C and C++ provide special commands called jump statements to handle these exact situations.
Now that we understand what jump statements are, let us look at our first tool, the break statement. Think of the break statement like an emergency exit door in a building. The moment you walk through that door, you are completely outside, no matter what you were doing inside. When the computer encounters a break command inside a loop, it immediately stops executing the body of the loop. It then jumps straight to the first line of code immediately following the loop. This is incredibly useful when you are searching for a specific item in a large list of data. Once you find it, there is no logical reason to keep searching, saving valuable processing power. Before we see the break statement in action, let us understand the mathematical setup of our loop. Every counting loop needs a starting point, which we define by initializing a counter variable. Here, we set the variable I equal to 1. Conceptually, this tells the computer to allocate memory and begin our counting process at the very first step. The variable I represents our current position, and the number 1 is our starting value. If we were to increase this starting value, our loop would simply begin its search later in the sequence. This simple assignment is the foundation that allows our loop to track its progress before we introduce any jump conditions. With our counter initialized, let us see this with a concrete example. We are given a task to count from 1 to 10, but we are asked to stop completely as soon as we reach the number 5. We set up our loop to count upwards, one step at a time. Inside the loop, we use a decision-making statement to check the current number. The computer first verifies that our counter is less than 10, which allows it to enter the loop. It then checks if the counter equals 5. Since our starting value is 1, this is false, so the computer prints the number and prepares for the next step. Continuing with our example, we must advance our counter. We do this by setting I equals I plus 1. Why is this step necessary? Because without it, we would be stuck at 1 forever. The loop repeats smoothly, printing 2, 3, and 4. But when the variable I finally becomes 5, our internal condition is met. The break statement is immediately executed by the computer. The loop terminates instantly. Physically, this means the program execution jumps completely out of the loop structure. As a result, the numbers 6 through 10 are never printed, and the program simply moves on to whatever instructions come next. Now that we have successfully used the break statement, we must discuss a very common trap. Beginners often make the mistake of using a break statement inside a switch statement that is itself placed inside a loop. A switch statement is a decision-making tool that selects one block of code to execute from many choices. By design, every switch case usually ends with a break to stop it from spilling over into the next case. However, if you want to exit the surrounding loop from inside that switch, the break statement will not work as you expect. It will only exit the switch statement, leaving you still trapped inside the loop. We will need a different technique for this. This limitation of the break statement brings us to our next jump command, the continue statement. While break acts as an emergency exit, the continue statement acts more like a skip button. When the computer encounters a continue statement inside a loop, it immediately stops executing the rest of the code in the current repetition.
However, instead of destroying the loop entirely, it jumps straight to the next repetition. Think of a teacher grading a stack of exam papers. If a student was absent and handed in a blank sheet, the teacher does not stop grading the rest of the class. Instead, the teacher simply skips that blank paper and moves on to the next student. This is exactly what continue does. Before we apply the continue statement, we must understand a critical mathematical requirement when using it inside a while loop. In a standard counting loop, the increment happens automatically. But in a while loop, the continue statement jumps directly back to the condition check at the top. Therefore, we must manually update our counter using the formula C equals C plus 1. Here, C is our counter variable and we are increasing it by a step size of 1. If we fail to increase this variable before the continue statement triggers, the condition will remain exactly the same. The physical result is a frozen program, trapped in an infinite loop, repeating the exact same step forever. Let us see how to safely use continue with a concrete example. We are given the task to print numbers from 1 to 5, but we specifically want to skip the number 3. We set up a while loop with a counter variable c starting at 1. Inside the loop, our first action is to check if our counter is equal to 3. For the numbers 1 and 2, this condition is false. Because it is false, we bypass the continue statement and print the numbers normally. We are carefully managing this counter to avoid freezing the program, setting the stage for what happens when we actually hit our target number. Continuing with our skipping example, we reach the critical moment. After printing 1 and 2, we always increase the counter by 1. When C becomes 3, our skipping condition finally becomes true. Now, why must we be extremely careful here? Before we execute the continue statement, we absolutely must increment C to 4. If we forget this step, C will stay 3. The continue will jump to the top, the condition will still be true, and the program will freeze. By incrementing C first, the continue safely skips the printing step for the number 3 and routes the program directly back to the top to test the number 4. The final output is 1, 2, 4, and 5. To solidify our understanding, let us look at this flowchart comparing the two statements. On the left, we see the break statements path. Notice how the arrow from the break box completely severs the loop cycle, pointing straight down to the end of the loop. It forces the program to move on to whatever code lies beyond. In contrast, look at the continue statement on the right. The arrow from the continue box does not exit the loop. Instead, it merely short-circuits the current cycle, routing the program directly back up to the condition check diamond to see if another cycle should begin. This visual perfectly captures the difference between an emergency exit and a skip button. Now that we have visualized the standard jump statements, we must address a controversial command, the goto statement. The goto statement is the oldest jump command in programming history. It tells the computer to unconditionally jump to a specific labeled line of code anywhere in the current function. Imagine playing a board game where a card says to go directly to a specific square, ignoring all rules in between. While it seems powerful, modern programmers strongly discourage using goto because it creates what we call a spaghetti code. Spaghetti code refers to programs where the execution path jumps around so chaotically that it becomes impossible to read, debug, or fix. Historically, its only acceptable use was escaping deeply nested loops. Since we want to avoid spaghetti code, what is the modern alternative to goto? We use a flag variable. Conceptually, a flag variable is a simple true or false indicator, much like a physical mailbox flag that is raised when you have mail. Mathematically, we initialize this by setting a variable, let us call it f, equal to 0. Here, f is our tracking variable and 0 represents the Boolean state of false. This means we have not yet found what we are looking for. If we change this value to 1, it represents true. By checking this single variable, our program can gracefully shut down multiple layers of loops without ever needing a chaotic goto jump. Let us see how this flag variable works in practice to escape nested loops. We are dealing with an outer loop and an inner loop. First, we add our flag variable to the condition of the outer loop. We program the outer loop so that it will only continue to run as long as its normal condition is met and the flag f is still equal to 0. This sets up a dual lock system. Then, inside the inner loop, we perform our actual search for the target data. As long as we do not find the target, the flag remains 0 and both loops continue to cycle normally.
Continuing with our nested loop search, we finally locate our target data. The moment we find it, we change the flag variable f to 1, which represents true. Next, we use a standard break statement to exit the inner loop. When the inner loop breaks, the computer naturally goes back to the top of the outer loop to check its condition for the next cycle. But remember our dual lock system? Because our flag f is now 1, the combined condition is no longer met. The outer loop terminates naturally and gracefully without any chaotic jumps. This method completely avoids the go-to statement while achieving the exact same result in a clean, readable, and professional way.
We have covered a lot of ground today, so let us review our key takeaways. First, jump statements provide essential flexibility, allowing us to break the rigid rules of standard loops when real-world problems demand it. We learned that the break statement acts as an emergency stop, completely terminating the loop when a specific condition is met. We also saw that the continue statement acts as a skip button, bypassing the rest of the current iteration and moving safely to the next one. Finally, we discovered that while the go-to statement exists, using a flag variable is the modern, professional standard for escaping complex nested loops without creating messy, unreadable code. You now have complete control over your program's flow.